Welcome everyone to today's webinar. I'm Celia Merzbacher. I'm Executive Director of the Quantum Economic Development Consortium, or QED-C, and it's a delight to be hosting an event today that's clearly of high interest. We got a lot of people signing up as soon as we announced it. Thanks for your flexibility. I think we had to reschedule it, but delighted to see so many people here with us today to hear from an outstanding panel about the intersection of quantum computing, and AI. I think this is a topic that's on top of mind for a lot of people, both experts and non. So I think we probably have a diverse audience, and I look forward very much to hearing from the panel today about both what quantum computing might do for AI, what AI might do for quantum computing, and then the nexus of the two. QED-C did a study, an assessment late last year. We're just now publishing that report first to our members. A benefit of membership in QED-C is early access to our reports. If you're interested in knowing more about becoming a member and you're not already, please go to our website for more information there. But you can look forward to a public version of the report that will be released in about a month. So with that, I'd like to turn it over to the moderator of today's panel, Sierra, for introductions of the panel. Sierra, over to you.
Awesome. Hi, and welcome to our panel discussion. My name is Sierra Shukair. I'll be the moderator. I'm a quantum journalist and data analyst at the Quantum Insider, and I'm really excited that we get to have this conversation with this panel of experts. So with that being said, I'd like to introduce Dr. Alain Chancet. He's the president of Molket. He has over 30 years of experience in enterprise. He's a senior member of the IEEE and co-author of the book Quantum Chemistry and Computing for the Curious. I have Dr. Bob Kuka, chief scientist at Quantinuum, distinguished visiting research chair at the Perimeter Institute, former professor at Oxford, author of Quantum in Pictures, and accomplished musician. Professor Damir Kava, associate professor at Indiana University Bloomington. He directs the Natural Language Processing Lab and organized the Quantum NLP Study Group. And Dr. Taha Salem, he is the general manager of Molket and the lecturer and quantum education officer at the Amsterdam University of Applied Sciences. Sorry about that. Okay, and with that being said, I'd love to go ahead and jump into our first set of questions, which is meant to explore both the current state of quantum computing and AI, as well as the synergies of quantum computing and AI. So starting with you, Bob, I'd like to ask, the upcoming report, highlights the complementary relationship between the two emerging technologies. So from your perspective and experience at Quantinuum, how are you seeing these two fields converge in practical applications, especially as it relates to quantum natural language processing?
So thank you, Sierra, for the introduction, talking to us. So personally, I wouldn't call it convergence. Convergence is sort of where things just flow to each other, which is actually not the case here. There's a few paths you can take. Like in first order, you can ask, like, how can AI help quantum? And that's quite a straightforward case, I think. Like the standard AI methods, as we know now, are already helping in many domains, like be it like quantum error correction. I know that people are looking for new algorithms, looking like typical machine learning methods. And a lot of people who used to work in quantum machine learning actually a little bit secretly moving to AI for quantum, like how AI can help quantum. Now, the more tricky direction would be quantum for AI. Quantum for AI, as we know, there's been a lot of effort in there with what I would call vanilla machine learning. But a lot of people have left the field, to be honest. Not necessarily because it doesn't work, but the nature of that field is that it has to be empirical. So one has to wait for the big machines to see if things work, because there's simply no theoretical underpinning at the moment in most places which guarantee that you're necessarily going to get some positive outcomes. No, I mean, I'm personally active in how quantum helps AI, but we kind of follow the path which may be quite unconventional as we are doing it now. So one area where we know quantum will help AI, and that's because, I mean, that's where Richard Feynman coined the term quantum AI, is chemistry. So we know a chemical process involves like exponentially growing spaces if you want to simulate the thing. And typically, you're dealing with quite complex, what people call tensor networks, which are highly entangled, and they're incredibly difficult to simulate. They're basically impossible to simulate, to be honest. And the closest you can get is actually with a quantum computer. And so we rather than doing the sort of uh, what people in machine learning do, black box approach, like unstructured black box approach, we have been embracing the structure of language, even further working on it and further exposing it. And language is kind of a process, you know, like when we are speaking, when I'm speaking to you, I mean, I refer to certain nouns and terms, and then I kind of entangle them. I'm just entangling quantum and AI, by the way. I say, oh, quantum is connected or converges. These are different ways to entangle quantum in AI. And every sort of terms I use, I'm entangling stuff. So I'm basically building a quantum process up here. We're in the same situation as chemistry. It's going to be difficult to simulate. And that's the kind of thing we did. And this also appeals to a current demand or desire from many stakeholders in AI, is that we make AI more understandable and interpretable and accountable and all of these things, because accidents may happen. And if we look at the history of science, a thing which we don't understand usually bled to death. We've seen this in many occasions, like really like the Babylonian science and things like that. Many cases when you had very successful science, but we didn't really understand what we're doing. At some point, it dies. And so that's my approach. And in some, okay, I said AI for quantum, quantum for AI, but even in what I'm saying, it's already like some sort of mutual interaction, because AI is obviously helping with the encoding of data, which is a difficult case as long as that we don't have anything like quantum RAM. And yeah, I mean that's pretty much what I have to. Okay, yeah, like we have theoretical results now that you would get exponential speed up, and that's because we went for the chemistry path, where you kind of can expect that. So anyway, that's the sort of thing we are specifically doing here at Quantinum. There's other people working on AI for quantum. There's some other things like being started now, but that's sort of the thing we have been doing for the longest. And this
Awesome.
goes back to Oxford University, 2007, 2008, by the way.
Thank you for sharing, Bob. I also really love that you called out the quantum chemistry piece. We did mention in the report as well that chemistry and material science applications have high potential as they inherently involve quantum phenomena, and quantum computers we hope are best suited or naturally suited to model those. So on that note, still talking about the synergies of quantum and AI, my next question is for Dr. Damir Kevar. The QED-C report does highlight the potential of hybrid quantum computing and AI approaches. Your work at Indiana University brings together natural language processing with quantum computing. Can you share how your research and specifically the natural language QKit aligns with hybrid approaches, and what unique and challenges you've encountered in quantum NLP?
Some of that Bob already mentioned, and I want to emphasize, by the way, our motivation to restart working on NLP with quantum instead of just classical started actually with Bob's work and all the papers that he published over the recent years with his team at Quantinum and colleagues in Europe who were organizing the QNLP conference. This was a trigger for a lot of my students and for myself as well. So the hybrid approach, just to give you an impression of a very simple experiment that we were working on, that has to do with using ChatGPT style algorithms and data and models. Also Claude 3, if you know these models as well, similar. What we tried to do is basically, or we did, we took the vectors, the words, tokens in language are mapped into vectors of a fixed length. In GPT, for example, they use more than 3,000 dimensions. with real numbers as vectors. And if you encode those in a normal classical computer, you're required for every single token to store the information in about 100,000 classical bits. And this is, of course, when you're thinking about the models as such, when you provide a space in the transformer models for input of, say, 128,000 tokens, that's a huge data structure that these models have to process and store. That has to be trained as well. And so what we try to do is figure out, can we transfer this into a quantum computer? And what does this mean? These vectors usually are trained to reflect semantic properties. So you would have a vector for cats and a vector for dog, and they would be more similar using distance in a semantic space, linear algebra measures, than cat and car, for example. And the question for us was, if we transfer these models into a quantum space, into a real physical quantum computer, if at all possible, do we actually maintain the semantic properties of the classical vectors and models? Is the semantics still reflected in the distance that we can measure then in quantum computers? And one thing that I believe that NLP people did not or do not necessarily know is that you have the capabilities in quantum machines to store information in a very dense fashion. So we can compress 3,000 real numbers, 100,000 bits into 12 qubits on the quantum machine. And we can still compute with them. And these exist, actually. Quantinuum provides us a machine where we can compute with these embeddings. And these embeddings reflect then not just words, they could reflect texts, passages, books, and we could compute similarities between text and classification for text and so on. And we can do that already on quantum machines, physical machines, not just simulators. So there's a surprise effect here for a lot of NLP people when you tell them that you can compress the data down and you actually already have these qubits available. And then on the other hand, actually, when you really do that, you realize what the limitations are of quantum computing. And this is basically the interface between the classical world and the quantum world. Shifting the data around requires classical computation. We have to create the circuits and transfer them to the quantum machine, instantiate them, and then read back 1 bit as a result, for example, in a classification task, repeat this task very, very many times, and then estimate a probability function, a probability for a certain classification result. And so this is very, very complicated and takes a lot of time. And this is sort of the surprise effect for us after, getting in touch with real quantum hardware and experimenting with it, realizing where the limitations are. And we are now, of course, interested in basically improving these cycles, the interaction between classical and quantum computers, because on the long run, this will probably be the destiny of quantum computing. We will have to have hybrid systems that interact with each other. When you talk about AI, a lot of exercises and a lot of experiments that we read about and that we see at conferences are basically re-implementations of classical AI algorithms in the quantum world. And we just show that we can do it. But then again, there are these complications. If you want to have repetitive cycles, as Bob mentioned, if we don't have QRAM, we can't sort of store persistent information somewhere to optimize maybe the model or embeddings, for example. So we have to generate circuits, run them on quantum computers, generate some output, read it out in classical, optimize the circuits again, and repeat to basically run an experiment over months, for example, to get some reliable results. So this is the complication. And, the future is basically, for us, the insight is this has to be worked on. So we have to improve these interfaces with classical computers, and we have to actually, in fact, find very different AI algorithms and approaches on the quantum computer itself. I believe I'm certain actually that Bob's team is working on exactly that, talking to some of the people and himself. So yeah, thank you.
Thank you so much for sharing. That was very informative. I also love that you mentioned the QRAM part, because when I think of you, I actually specifically remember at the workshop you had made the comment that we need to give you more quantum memory. Like that's what we need. So thank you for sharing more about your work. And then I'd also like to turn this over to Dr. Salem as well as Alain Chancey. This is for both of you, so whoever would like to answer first. The QED-C report does identify chemistry and material science as high potential areas for quantum computing and AI integration. As an expert or as experts working with Molket and having backgrounds in quantum chemistry, how do you see these synergies manifesting in real world applications? And what timeline do you envision for meaningful commercial impact?
So let me put forward a perspective that complements those which have been put forward brilliantly. What we see is hybrid computation workflows, which integrate not just today's quantum processing units, which, by the way, hundreds of qubits and thousands of gates. So it's really much more powerful than it was just 3 years ago when my book came out. But really, today we also have to include high performance computing, supercomputers, and these hybrid computation workflows deliver value today. I mean, there are applications. There have been demonstrations, which means it's almost ready to be put to commercial use. And I would mention not just quantum chemistry, but also quantum molecular dynamics, material science, machine learning, generative AI. And by the way, Quantinuum has announced their generative quantum AI framework that harnesses unique quantum generated data to tackle complex problems which are impossible for classical computing. And so we don't have to wait for the emergence of large-scale quantum computing. Right now, and this is what we are working on at Molket, we view the added value of artificial intelligence and a robust, field-proven classical AI algorithm to learn from the output of both the high-performance computing and the quantum processing unit. So it's beyond just removing noise. It's actually learning. And the idea is that with AI, we can define so-called surrogate models that can accurately predict physical properties, such as the ground state energy, in the case of quantum chemistry, from the data which has been generated by a synergy of HPC and quantum processing units. Taha?
Yeah, thanks, Alain. So I would like to complement what also Alain has said, and also Bob and Dr. Xavier. Also, they have also nice works, pretty well known on that. It's quantum AI or AI work. I mean, the current workflows already integrating. Combining hardware of high performance computing, but also quantum, and there is a lot of use cases in this. And of course, NVIDIA is now trying to put forward the idea of universal function approximators, which sort of function where you, if the algorithm is quite complicated, then you can train an AI model or a little like a co-scientist agent on this particular algorithm. And mapping the inputs to the outputs, and then you can just have this algorithm to this function approximator to replace the complicated algorithm. And we can see a lot of current use cases. So I was quite astonished with a latest paper has been published recently, that already AI has developed or predicted a new protocol and a new quantum computing algorithm already. For instance, this protocol is about to create entanglement. So the experimentalists and the researchers were trying to create a particular swapping entanglement protocol, and they have trained an AI tool on several situations, and those are the available unknowns from the theory part. And when they did run it, they have expected to for this tool to come up with one of the situations that have been used in the training. However, this wasn't the case, and they got a new protocol. So they didn't think of. So that gives an idea about the potential of AI that with the current complexity, especially in chemistry and material design simulations, things that stops us from scalability to develop complicated Hamiltonians or complicated formalism could be actually achieved with an efficient, well-trained AI models that can help this at ease. Also, for example, we see also another use case from Google, where also they have already solved mysteries related to the protein structures and several atomic structures. IBM is also now putting forward supercentric computing, where it's already AI is integrated somehow in the hardware, and it now can deliver value and working mechanism. And Microsoft has already used it, and they have published it, like a paper by Matthias Troyer about, for example, the end-to-end simulations for chemistry. So we see a lot of progress in this. And I mean, that's already working around us. It's just a matter of how to use it and project it on the use cases that we are working with.
Fantastic. Thank you so much for sharing. So I noticed that as we went through those questions, each of you did add in a piece about challenges that you were seeing that you felt could move the field forward. And so just to review, Bob, specifically, I love that you mentioned this need for understanding, and that if we look back over the history of science, that we see where we have lacked understanding, those fields can eventually die out. And so it's important to emphasize the need to promote understanding. Professor Kava, you did mention that Bob's work was part of your inspiration to kind of bring back the quantum and the NLP at the university. And so I think that also speaks to the piece about understanding. We also talked about the need for more QRAM. And then we also talked about the need for better interfaces between classical and quantum technology. And so moving forward, another challenge that I'd like to call out that the report did highlight quite in depth is this need to promote education, as well as how do we come up with really solid plans for workforce development. And so keeping that in mind, I would like to see, Professor Demir, one of the key recommendations in the report is to increase research and education in academia. As someone who organized the Quantum NLP study group at Indiana University, how are you approaching this interdisciplinary challenge, and what have you found to be the most effective for bridging the knowledge gap between these two fields?
Yeah, thank you for the question. The study group that we organized was indeed actually, see, this all goes back to Bob, it's his fault. When we started working about NLP and AI, we triggered the interest basically from very, very different people all over campus. It started basically with cognitive science, psychology, because we have some colleagues working on cognitive models of reasoning, and they use actually quantum models for that, theoretical. We have NLP people, computer science people who are into that, into AI and natural language processing. And then we sort of got in touch with data science, computer science, physics, chemistry, mathematics, just to mention some. And now we have a heterogeneous group of people from all these disciplines coming regularly to meetings where we either discuss our own work or we discuss Bob's papers or some other work, and invite people, speakers, to present remote and local, in person. And what turns out to be very impressive for me. When I was a young student, I started off as a mathematics and physics student, and later was basically just fascinated by AI and natural language processing and changed into this direction. But the interaction with our colleagues from chemistry, for example, from mathematics and so on, helped us understand many things theoretically that we had no insights about. You could do quantum computing by just learning how to solve certain problems logically and implement certain gates and algorithms. Or you could go deeper and try to understand the physics of quantum mechanics and the applications and how you implement gates and so on. All these sides seem to be very interesting, and we bring people together from all kinds of disciplines. We have locally now on campus a quantum student club that is very active, also very interested in computation, that involves students from physics, chemistry, as well as cognitive science and computer science. And we have a new center that was established that is interdisciplinary, bringing together all the people from the different schools and departments who are interested in anything quantum. And this resulted in one existing quantum information science program, a master's program at IU, similar to other schools in the region that all started basically such an educational incentive. We did work on an NSF research traineeship program together, where I was gladly participating as a co-PI, where basically this component was also central. So we tried to integrate not just of the education at the level of hardware physics and quantum information theory, but also about AI and natural language processing and some other applied domains like cognitive science, modeling, and so on. So it can be fruitful. It works. We think that this domain of educating people in quantum computing who are already triggered and interested in AI is absolutely important for various reasons. I mean, my hypothesis is that quantum will change the environment. There are all these arguments that go about how quantum is more energy efficient on the long run. So some of our hardware providers argue that an exponential increase in compute power at the quantum level will be requiring just sublinear energy demand, while it's the opposite in classical compute environments. And we see that already. We hit the limits with modern AI systems, transformer-based type of GPT and so on. That is, on the long run, also not sustainable because of the amounts of data they need and the amounts of energy. So there are advantages, and hopefully this will somehow, if not in form of real quantum computing, but definitely in form of quantum-inspired computing in AI, trigger some changes and improvements on the long run. And yeah, we are working on these kind of interdisciplinary groups, and I believe that a lot of our folks are, I think my students and the participants in our group, which are also faculty members, are more and more convinced that quantum is a very interesting path to go.
Awesome. Thank you for sharing. I've considered that with quantum computing that you get these different backgrounds. You have physics and engineering, and you get more on the AI side, the computer science and the software. But I hadn't yet considered that there might be more interest among cognitive science and psychology as well. So that's really interesting. So also speaking on education and workforce development, my next question is for Bob. So the report does emphasize the need for expanding the quantum workforce and improving education. What approaches do you think are most effective for building this interdisciplinary workforce that understands both quantum and AI? And how might your visual approach, such as quantum in pictures, help address this educational challenge?
I mean, the origin of this is quite interesting in the sense that my initial motivation a very long time ago, going back to the 1990s, was to simply come up with a new language, new formalism for quantum. And this was following up on von Neumann's rejection in 1934 5, yes, of his own quantum mechanical formalism, which he only published in 1932 in a book, by the way. So this was only 3 years later. And I mean, in this quest, we started to use like category theory and high-powered mathematics, which first led to categorical quantum mechanics. But then quite early on, we discovered that this like single source of new quantum formulas, on the one hand, led us to the quantum natural language processing and recognizing that structures in language and also in cognition, by the way, since it was just mentioned, cognitive structure are actually very, very close to quantum mechanical structures if you just look through the right pair of glasses. And on the other hand, and that's basically through a connection made by Penrose a long time ago before that this kind of leads to a diagrammatic quantum mechanical formalism too. So initially we saw this diagrammatic, and then provocatively I wrote a paper in 1905 called Kindergarten Quantum Mechanics, never actually believing or hoping that you could come up with a full-blown diagrammatic quantum formalism, which we now know is possible. I mean, we've got theorems to show that any derivation of an equation you can do in Hilbert space, you can just do with our pictures, which you find in a book, Quantum in Pictures. So that's one thing. Then as some of you may know, like previous summer, but the summer before, we did an experiment where we showed that teaching this new language to high school students, basically, I had an interview about this with Physics World yesterday. We're going to do a blog post, a podcast specifically about this. We gave them this course. We mimicked an Oxford University postgraduate course. We gave them an Oxford postgraduate exam entirely existing of questions which had been asked at Oxford University postgraduate quantum courses. And the students kind of did better than the Oxford University students, which was kind of fascinating. So what this means is that this diagrammatic language is effectively a vehicle to teach a lot more people from different backgrounds into quantum, but it's not about different backgrounds. It's about starting early enough. Not just the background matters, but starting early enough when people don't really have like a direction or a background yet. Why is it important? Well, some result of our experiment was that the 15-year-olds did better than the 18-year-olds, which means the younger you are, the easier you assimilate this new way of thinking, which I think is very much more articulated in the pictures and the diagrams than it is in Hilbert space. For me, like Hilbert space is like zeros and ones, like the zeros and ones in computer science, while the diagrams are like a high-level language, which really tell you how you reason about programs. So it's quite a different reasoning. Some people say, oh, quantum is difficult, it's different than quantum, than classical. For me, this discrepancy between, say, the way Hilbert space is built up and most of Western science is built up, and then these diagrams of us, doesn't go back to like a bifurcation of classical quantum. It goes back 2,400 years to when Heraclitus and Parmenides disagreed, and then maybe Democritus disagreed with what later became Leibniz's view. So this philosophy goes much further, and it's really philosophy for me about processes and relationships, rather than about reductionism and a static picture of reality on top of which you then throw dynamics or something like that. So it's this completely different way of thinking which people need to get very early, and I don't think just quantum computing is going to be better of it. Also, the whole world is going to be better of it, because as humanity, we actually learn something from nature now, which make us think in a way which is much closer to reality, and which actually much closer not to reality, but also to humanity. Anyway.
Oh, thank you so much. I actually really loved reading about that experiment and hearing that the younger age group performed better. And it makes me think about, I didn't have exposure to physics or quantum mechanics until I was at the university level. So I'm really curious, if we start to introduce those topics earlier, even at the primary level, would we have students that are better prepared to deal with computer science in general, as well as AI and quantum? So very, very interesting. Still speaking on challenges, I kind of want to switch more to technical challenges. So I do have a question for you, Taha. With your background in quantum machine learning and chemistry, what specific technical advances do you believe are most needed in order to realize the potential of quantum and AI in materials discovery?
Thanks, Sarah, for the question. I would like first, before starting the answer, I would like to remind myself, but also a non-technical audience, about a typical workflow in quantum chemistry simulations. And the typical workflow, it just, for example, during my PhD, we were studying molecular collisions, and we need, for example, to describe the molecules, the molecular structure, but also the potential energy surfaces, how these molecules gonna interact with one another. And we have to develop a theoretical framework for that. So this is the first challenge: how we can come up with a good formalism to describe the simulation, and then how to transform this to a computational model in order to solve these things on the computer, and then choose the appropriate basis set, the kernel in which we are gonna do the solution, and several other works. But then once we perform the simulation, that will be done on HPC. We need also good administration of the code and the results, and also to perform post processing and also post analysis. Now we come to the computational complexity. When we do these things and these simulations on a molecular level, it's quite expensive, and so we are typically for small molecules like CO2 and like describing rotational and vibrational transitions due to collision with other thing that might take for one job like about for example 20 or 30 minutes. Sometimes we might need thousands of these jobs, so it eats up quickly a few weeks in calculations on a medium-sized cluster. So there's a lot of challenge here. So what AI can do, as all of the speakers have also were speaking in the beginning about the potential application of AI and the quantum, is that how to take the burden of the theoretical approximation and the theoretical development, and also how to reduce the computational complexity. And this now also in action, so it's happening. There's a lot of use cases supporting it. AI can help if it got trained on particular Hamiltonians and derivations, so it can help reducing the work that's been done on the theory part, like in automating the theoretical workflow. Also the mapping between the theory and the computational model. The second thing is the distribution, on which part can go to classical, which part can go to quantum, which part can go to GPUs, and so on. And then once we come to the quantum AI, for example, there is also use cases also have been put by Continuum and NVIDIA. Recently, NVIDIA also has published GPT-based model for class of algorithms for quantum computing. And could be helpful and reduce the computational complexity. So this is what I see, and we have in Molkit, we are putting forward use cases for this, and how to, for example, train AI agents in a particular Hamiltonian or a particular situation in order to ease certain computations, and also the synergy between quantum and AI, and in Continuum, and also in Microsoft and the Google, there is also similar very wonderful use cases as well.
Awesome. Thank you so much for sharing that. And then speaking on the technical challenges as well, the next question is for Alain Chancey. So something that the report did highlight, and that also Professor Kava touched on earlier, is that challenges in connecting quantum computers to classical ones to create networked hybrid systems hamper progress toward useful quantum computing and AI. So with your extensive enterprise experience, what other infrastructure challenges do you see as most pressing for organizations that want to implement hybrid quantum AI solutions?
Well, much progress has been done, and for instance, interconnecting quantum modules that is achieved by IBM, for instance, but of course, in order to scale to thousands of qubits, it's important to have the ability to effectively interconnect different quantum processing units. And but there are vendors which provide which offer solutions. So it's no longer applied research. There are already commercially available products for that. But I would say in terms of infrastructure, I would like to add the human dimension. It's a paradigm shift, as Bob pointed out. The way quantum algorithms work and the way to design them is radically different from the classical one. And so it's not just an infrastructure challenge. It's also on the human side having the critical mass of expertise to bring together experts in high performance computing, quantum computing. So this is what has been achieved by IBM. So when I attended the IBM Quantum Developer Conference, the manager in charge of the future of quantum computing came from the high performance computing world, which is essential. And as Tara pointed out, integrating AI in the mix, but to make it also easy from the user standpoint. The end user standpoint shouldn't be scared by shouldn't have to deal with the apparent complexity of integrating those different pieces. And this is what's already available out of the box with Qiskit runtime and Qiskit functions. There are building blocks which are there with APIs. So it boils down to skills and knowledge how to put together these different building blocks. I would like to point out that successful architectures, particularly in chemistry lab automation with AI agents, can be extended very logically to quantum AI agents, where in the mix among AI agents, there would be a quantum processing unit, but packaged, seen as another agent, a quantum AI agent. And beyond that, we can envision today with existing technology in quantum sensing, quantum communication, that is connecting different units in a pure quantum way, and quantum processing. We can already today envision quantum AI agents, independent, autonomous agents that can run, for example, chemistry and combine the best of what we can offer today with generative AI and quantum processing and high performance computing and quantum sensing. So I think this is so the challenge in terms of infrastructure. I would say it's more on the human side to train and put together a multidisciplinary team which can make it happen, have this synergy of the best of breed of different components. Thank you.
So thank you so much. Thank you all for those considerations as we looked at the different challenges. So just to kind of capture what we've spoke about so far. So we've talked about the potential synergies between the two technologies. We highlighted the technical challenges, the need to revisit education and workforce development, challenges with infrastructure, and as Alain Chancet mentioned, also a need to consider the human dimension. So all of that aside, the QED-C report does offer 3 key recommendations for moving forward. So one is including support for quantum and AI in federal initiatives. 2 is increasing quantum and AI research and education in academia. And 3 is connecting industries to accelerate technology development and adoption. So with those 3 recommendations in mind, my next question is presented to all of the panelists. Which of these do you think would have the most immediate impact if implemented, and why?
I can say something.
Yeah.
I don't think it's about which. I think it's about how.
Mm.
So all of these 3 can be either successful or fail, depending how it's implemented. Like, I mean, there's a long history of interdisciplinary research, and then interdisciplinary research, which this is about, like bringing things together, has been like one on the surface of the other. or it's like one kind of like computer science for a long time was sort of the surface of other sciences, and that usually doesn't work. What we need here is somebody who basically, I mean, it's been also emphasized by my colleagues after I said this. We need people who think in a different way and can basically embrace both aspects at the same time, the reasoning, the cognitive science, and then that's where Damir, like we sort of approach where people try to understand each other, is actually more fruitful than basically some official saying, okay, you people should now work together, because that never works. That never works. I mean, I've seen this too many times in the past. It just doesn't work. So it's really a matter of how you're gonna try to achieve such a synergy. And my personal approach, like I built a big group initially at Oxford, like starting in 2001 till 2020. And this was a mix of people with computer science background, people with cognitive science background, also people with mathematics, with philosophy, everything together. And then people at PhD level, they start to talk to each other, they start to train each other, they start to understand each other's language and concepts and reasoning. And that's how I think you can get new things that are generally about thinking outside of the box. Of course, if you're talking about combining high performance computing and quantum computing, you need serious domain specialists, of course, involved who can talk each other. So that's a different thing. But like I would say on a theoretical level of coming with new applications, you really need a new kind of scientist, not just putting two together.
No, thank you for sharing.
I could add to that. Actually, I agree totally with respect to creating heterogeneous groups. In particular, you know, when we are talking about what we need is a completely new paradigm we need new algorithms. Actually, there was a stagnation of innovation of algorithms at the quantum side for a while now. And you know, we are all waiting for Peter Shor to come up with a new one. And you know, what has to happen is there has to be more investment, and the more people we get involved, the more likely it is that we will have new ideas and algorithms that are successful. The other side that is important, I think, is the third point, and this is, you said, connecting industries to accelerate technology. I think what we need to do is connect all of them, connect academia and industry, because the problem, as with AI, you see that we are developing a monopoly where basically the infrastructure to do successful experiments with advanced AI algorithms and systems and models, the monopoly is clearly just with industry right now. And at academic levels, we can't even compete or participate in the academic in the research scientific discussion about that. And so having partnerships with academia and industry would be sort of the solution on the long run to facilitate research scientific activities within the academic community, having professionals providing access to hardware and so on.
Yeah. I can add also to this. So, as Bob and also Damir have pointed out, these are really great points. I would like to touch upon the federal initiatives for education. I mean, also we have as like working in academia, but also we together with Alan, we have our own startup. We are involved in several educational programs, and for example, in the Netherlands, when we do workshops, we see the enthusiasm of people. So people come to work together. There is friendly settings so people can express their ideas, share their views, and always the more you have, the more people you have, the more fresh ideas you gain, and the more knowledge you get. So that's pretty fascinating. And also for Molcat, for example, we are co-organizing a monthly series, and it has been attended by people from different places, like in Egypt and several places in Middle East and in Europe and Latin America as well. And you see always how people can collaborate together in hackathons and teaching one another, as Bob have indicated in his research group. And this kind of things overcome the technicality and the competition, the challenges of their domain knowledge. So everyone from computer science will teach one from physics, and so on. And I have also a YouTube channel, and I see comments from high school students and undergraduate students. I have two YouTube channels, one in Arabic and one in English. And all the time, people get more enthusiastic about quantum. from just seeing the momentum and seeing the activity. So I would say that such increasing such federal initiatives would help the second 2 points, because the people will understand the technology more, but also they will have the good skills to work hand in hand. And the second thing, if we once this educational momentum is gone, it also helps increasing the talent pool. So now we see, of course, all quantum activities and the initiatives have increased the competence level of the graduates, and also university graduates, master graduates, by even 10%. And that has been reflected on those people also open companies, they hire for new jobs. So that has increased the job market, even as some reports from McKinsey and some other consulting firms, they say about 9 to 10%. So that's quite impressive. So hopefully the federal initiatives in the states, but also in Europe and in other places, once they increase and there is more collaborations, then that will enhance the whole quantum ecosystem.
Awesome. Thank you so much. I especially love that you highlighted federal initiatives as a way to potentially bridge that gap between education and then using it to help develop the workforce. So that's very interesting. Awesome. Any more comments on the 3 recommendations?
I would like to add that consortiums, organizations like QED-C and QUIC in the European Union, and there is a similar one in Canada, are really help create these encounters between different fields of expertise and users business, because startups, especially in quantum computing arena, are pushing their solutions, looking for problems. But so that's a push approach. But in addition, that the business should pull and invite, create challenges, invite solution providers to come up with innovative, disrupting solutions to deal with their challenges. So I think, in addition to federal help, initiatives which are actually cross-border beyond federal, where QED-C and QIC, QUIC, they make it possible to have a collaboration between different countries. And I think that's a key success factor as well.
That makes a lot of sense. And the QED-C was born of federal initiatives, and it does help bring together a lot of those different companies and different parts of the industry and academia, et cetera. So that's really great. Okay, so it looks like we have about 5 minutes left. I do see that we have a few audience questions. There's 8 of them. I don't know if we can get through all of them, but curious if we would like to answer a few of those. Let's see. I can arbitrarily pick out a few. Let's see. Actually really love this question that just came through the chat. So Selma said, what would you recommend those who work in education to start aiming at in order to focus on quantum education? What is a gap that universities are not currently filling or cannot fill?
I can start making some comments. One of the gaps is actually the professors. So we need actually teachers, and so this requires that we start educating the new generation of academics who can teach. And so yeah, there's a lot of needs. It's hard to get these experts, and then when the industry is competing and you're sort of offered a low-paid academic job compared to a high-paid industry job, then you have to make your choice, and that's difficult. There are a lot of such issues right now. It's not just quantum, it's AI as well, actually. So
awesome.
It's like I said earlier, it's in line with the fact that it's such a different way of thinking. And we, like one, of course, can approach teaching quantum like in a way like as much as it looks like classical computing, which is what usually most people doing if they want to try to educate quantum. So it's actually not that different from classical. Like think with this sort of thinking, you're never going to come up with something new. You just maybe feel, okay, maybe it's not that difficult, but that's the typical way it starts. And that's what typically like traditional teachers would do, because it's really not easy if you've been trained your whole life in a particular way of thinking to actually start from scratch. And I think we're really at the very beginning of quantum thinking and quantum education. And if you, in 10, 20, maybe 30 years, going to completely look different in ways we kind of really can't predict now. But it's always been like that. One tries to stick to the past too much most of the time. Well, whereas to jump and make a big jump to the future of what it could be. Even sometimes if one is wrong, it's not a problem.
Yeah, thank you. I do want to take note that we are getting close to time, and I wanted to just take the time to thank the panelists as well as the attendees and see if there are any last comments you'd like to leave our audience with before we close out the panel.
Yeah. Thanks everyone, and
Thank you.
yeah, thanks Sarah, and I was glad to be among with you in this nice panelist. Was Ala, Bob, and Damir, and also with Amia and Celia as well. So thanks for the nice panel, and looking forward for future events as well.
Thank you.
Yeah, thank you.
Thank you all.
Bye.
Bye.
Goodbye.
Goodbye.
And thank you to our panelists. We appreciate your time.